Good morning, everyone. Today, I'm going to discuss an important concept in classification, that is confusion matrix. So, whenever we implement a classification model, whatever the algorithm it may be, at last, how we are going to say that algorithm is the best model? Our model, what we have used for classification problem is the best model. For that, we have to evaluate a classification algorithm. For that, we use some matrix. That matrix is being given by a matrix called as the confusion matrix. So what is this confusion matrix? A confusion matrix is an n by n matrix used for evaluating the performance of a classification model, and where this n is the number of target classes. This confusion matrix compares the actual target values with the predicted target values. So how it confusion matrix looks like is something like this. So we have these four variables in this, and these are actual values, these are predicted values. And this confusion matrix, it is a technique for summarizing the performance of a classification algorithm. And this matrix helps us understand what our classification model gets right and what sorts of errors it makes. And at last, it is the predictions what we made with the actual data. It is going to give us a conclusion whether our model is a good model or not. So this is the confusion matrix. Confusion matrix presents a table layout of different outcomes of predicted and results of a classification problem and helps visualize its outcome. So it helps us to identify the correct predictions of a model for different individual classes as well as the errors. Now, see here, a confusion matrix as a matrix itself consists of rows and columns. In the same way, confusion matrix also consists of rows that contains the predicted values. These rows contains the predicted values predicted by the classifier, and the columns which contain the actual values, that is from data set. The actual values of our data sets are along the columns, and the values predicted by our classifier are along the rows. Now we are going to fill, once we have built some algorithm, classification algorithm, we have built with any algorithm, at last the outcome of that particular classification algorithm is, it is going to give us this confusion matrix with all these values. Okay. So let us explain this confusion matrix with one example. Consider a confusion matrix made from a classifier which classifies people based on whether they speak English or not. Now we have some set of data where in that set of data there are people who speak English and there are people who doesn't speak English. Now our classifier has to identify correctly who speaks English and who does not speak English. Let us see how it is going to identify and what it is going to give. So when a people who can speak English and actually positive and predicted is positive, then we call it as the positive. Suppose our classifier has identified the people who can speak English and actual also those people speak English, that we call it as the true positive. Okay? And people who cannot speak English will be classified as negatives. That is, there are some people who can't speak English and actually also they can't speak English. So those are called as the true negatives. Okay, hope you understood. If our classifies identifies the people who are speaking English exactly, then that is called as true positive. And if it predicts the people who can't speak English exactly like actual value, those are called as the true negatives. See here, the number of times our actual positive values are equal to the predicted positive values gives us the true positive. Okay. Suppose there are 10 people who speaks English and actually is also 10 people, and our predicted also given that 10 people are speaking English, then we call it as the true positive. Similarly, the number of times our actual negative values are equal to the predicted negative values gives us the true negatives. Who can't speak English, even actual also they can't speak English. Those are called as the true negatives. And there are two more things are there, that is false positives. So what do you mean by this false positive? Actually, they can't speak English. In actual, some people can't speak English, but our classifier predicted that they speak English. So those are called as the false positive. Okay, they can't speak English. Actually, some people can't speak English, but that some people, our classifier has identified that they speak English. So those are called as false positives. And there are some people who actually speaks English, but our classifier predicted that they can't speak English. Those are called as the false negative. Try to understand. Actually, they speak English, but our classifier predicted that they can't speak English. Those are called as the false negatives. Okay. And if actual is positive and predicted is positive, true positive. Actual is negative and predicted is negative, it is true negative. Actual is negative, but predicted is positive, it is false positive. Actual is positive, predicted is negative, those are called as false negatives. So these four are very important terminologies in a confusion matrix. Identifying true positive, true negative, false positive, and false negatives are important things in constructing a confusion matrix. Okay, see here, false positives and false negatives. So this is the actual confusion matrix. So when you see a confusion matrix, we'll have actual and predicted. And from that, we'll derive true positive, true negative, false positive, and the false negative. Now, it's time to evaluate the classification algorithm. That is, confusion metrics are the performance measures which helps us to find the accuracy of our classifier. Now, from that confusion matrix, we have to find out four important metrics. There are four important metrics. That is accuracy, precision, recall, and F1 score. Okay, how we are going to find out? How we are going to say that our classification is accurately classifying the two different class levels. So accuracy is used to find the portion of correctly classified values. That is, it tells us how often our classifier is right. That is, it is sum of all true values divided by total values. So when you see this confusion matrix, what are true values? Yes, these are true values, true positives, and true negatives, and divided by all values by total values. That is true positive plus true negative divided by TP plus TN, FP plus FN. This is how we are going to find out the accuracy. So to find out this accuracy, what we need, first we should construct a confusion matrix. From confusion matrix, it is very easy to find out all these metrics. Then precision. Precision is used to calculate the model's ability to classify positive values correctly. It answers as a question, out of total predicted positive values, how many values are actually positive? Okay, out of total predicted positive values, how many are actually positive? That is, it is true positives divided by the total number of predicted positive values. That is true positive by true positive plus false positive. Okay. This is what the precision. Then recall. Recall, it is used to calculate the model's ability to predict positive values. That is, out of total actual positive values, how many positive did we predicted correctly? Okay. Out of total actual positive values, how many positive did we predicted correctly? That is given by this recall. So it is true positives divided by the total number of actual positive values. So what is that actual positive values? When you see this confusion matrix, you can see that TP by TP plus FN. Okay, that is TP divided by TP plus FN. This is given by the recall. Now, let us solve one problem. This is some data we have collected for a particular model. And these are the predicted values and these are the actual values. And asking us to find out the accuracy, precision, recall, and F1 score. So this is the problem statement. Consider the confusion matrix of a binary classifier. Yes, how we are saying that it is a binary classifier? Well, because we have only two labels. We got 4, 2 square into 4. So the classifier made a total of 150 predictions. And out of those 150 cases, the classifier predicted yes 100 times. So when you add this 100 times and no 50 times, so 45 plus 5, 50 times. No 50 times, 100. Yes, yes, 100 times. And this total is the, when you count all this, it is total 150 predictions. So in reality, total is 150 patients. In that 100 patients have the disease and 50 patients do not have the disease. So when we have feeded this information to a particular classification model, how accurately it is predicted? Let us see by solving all these, by calculating all these metrics. So the first one is, so this is true negatives, true positives, false positives, and false negatives. So when actual S and predicted S, we know this is true positive. When actual no, predicted no, it is true negative. Actual no, predicted yes. This is false positive. Actual yes, predicted yes. Okay, that is true. Actual yes, predicted no, that is false negative. Now, the very first one is accuracy. We know that accuracy is given by number of positive values by total number of values. That is true negative plus true positive plus true negative divided by all these things. So we got the accuracy is 93.33%. That is accurate. It is 93% accurately. It is classifying actual as actual, predicted as predicted. That is what this accuracy. This, if you get above 90%, now our model is the good model. And next, misclassification rate. So how we are going to identify the misclassification rate? That is, for accuracy, we have taken these two. For misclassification, we are going to take these two. That is false negative plus false positive divided by total number of outcomes. And one more way how we are going to find out this misclassification rate is, it is also given by error. Misclassification rate is nothing but error. That is 1 minus accuracy. So we got already 93.3. So 1 minus 93.3, you get 6.67. So 6.67 means we have very less error rate. So we can conclude that our model is the best model. Then next one, true positive rate. This is also called as sensitivity or recall. So when it is actually yes, how often does it predict yes? That is what the true positive rate. So true positive rate is given by true positive divided by actual yes. That is this one. So true positive is 95 divided by 100. Why? Because 5 plus 95. That is 95%. Our positive rate is 95%. Then false positive rate. When it's actually no, how often does it predict yes? Okay. So false positive rate is given by false positive divided by actual no. Okay. False positive divided by actual no. False positive is 5. Actual no is 45 plus 5. That is 10%. Yes, means we have very less false positive rate. Then true negativity rate. Then it is also called as specificity. When it's actually no, how often does it predict no? Is known as specificity. True negative rate is true negative divided by actual no. So that is 45 divided by 50. 90% means 90% of the time, if it is no, actually is no, even our prediction, our classifier prediction also no. That means we have very good accuracy. Then precision. When it predicts yes, how often it is correct? So that is given by, precision is given by true positive divided by predicted yes. Predicted yes is 95 plus 5. That is 95 divided by 100. Yes, 95% of the time what we predict yes is correct only. It is almost equal to the actual. Then one thing, F1 score. That is one more important metric for F1 score. So even though we have accuracy, precision, recall, why we need this F1 score? Yeah, I'll explain you with one example. Before that, let us see. F1 score is one of the common measures to rate how successful a classifier is. And it's harmonic mean of two metrics, that is precision and recall. That is 2 into precision into recall divided by precision plus recall gives the F1 score. Now, let us see why we require this F1 score. We have calculated different metrics like accuracy, precision, recall. Still, developers want to find out F1 score. We know that accuracy equal to total number of predictions made by total number of predictions. Suppose if we have a balanced data set, okay? I think you know what is balanced data set and imbalanced data set in classification discussed. Suppose you want to classify two labels A and B, and in a data set, if you have exactly 50-50% of say labels, then we can say it is balanced data set. Suppose A, you have 90 labels and B have only 10 labels. Then of course this is called as the imbalanced data set. So when our data set is imbalanced, if you are calculating accuracy, it doesn't give us the accurate results. Why? Because it is imbalanced data set. So at that time, there is a need, if data set is imbalanced, we can't alone use the accuracy as the metric. We also has to use precision and recall, and along with that we should also use the F1 square. So we already discussed what is precision and what is recall. Precision is, we know that it is true positive divided by true positive plus false positive, and recall is true positive divided by true positive plus false negative. Now you may get a doubt that when we have to use the precision and when we have to use the recall. Okay, for some applications, only we have to concentrate on precision. And for some applications, we have to concentrate on recall. Let me tell you with one example. Suppose here we should focus on precision. Why we have to focus on precision is, suppose if male is not a spam mail, male is not a spam mail, but our classifier is identified it as a spam. That is false positive. That is not a spam mail, okay, but our classifier identified it as a spam mail. So for such application, for such a problem statement, this false positive is important. So whenever there is an false positives are more important, then definitely we have to use the metric precision. Remember, when for a particular application, if false positives are important, then go for precision. Then, why? Because we have to reduce false positive. If it is not a spam mail, no single wanted mail should go to a spam folder. That is what the agenda while we are implementing a spam filter. So we have to reduce false positives. For that, we have to use a precision. Then, coming to this recall, let us take one example of a problem statement. You want to calculate, you want to say whether a particular person is having cancer or not. At this time, what is important? Whether a person is having cancer or not. Then here we have to reduce the false negatives. Here the agenda is to reduce false positives, spam detection. Here the agenda is to reduce false negatives. Why? What is this false negative? Why we have to concentrate on this? Suppose if the person is having cancer, model has predicted the person is not having cancer. Just think of how blunder mistake our classifier has made. Person is having cancer, but our model predicted that person is not having cancer. So it's a blunder. Our classifier has made a blunder. So in that case, so this is nothing but what person is having cancer, but our classifier has predicted he is not having cancer. So it is nothing but the false negative. And here you may get it out. Then what about false positive? Why we are not taking false positive important for this particular problem statement? Suppose person is not having cancer, but our model has predicted that particular person is having cancer. Of course, person is not having cancer, but our model predicted he has cancer. Okay, let it be. He will go for second chance, second doctor, and he will confirm that he is having cancer or not. But in the very first stage, if you say that a particular person is not having cancer, then he will sit and relax. How much blunder our classifier is making, just think in that, just analyze that one. So in such cases, our main intention is to reduce the false negatives. So whenever for a particular problem statement, our agenda is to reduce false negatives, then we should concentrate on recall, finding recall. How much good accuracy, how much above 95% if your recall is, then that much accurate your classifier is. And how much accurate your precision is, if it is more than 95%, that much accurate that spam filter is. Likewise, depending upon the problem statement, we have to give importance to, we have to calculate precision and the recall. And suppose you may get a question, doubt. In some cases, for some particular problem statements, yes, of course, we need have to give importance to both false positive and false negative. Then what we have to find out? There is a question. If it is false positive, we are saying precision. If it is false negative, we are saying recall. There is a situation comes where both false positive and false negatives are important. Then what we have to find out? Yes. There the comes into picture, that is F1 score. Okay. We have to find out F1 score. F1 score is, it is nothing but 1 plus beta precision into recall by beta square P plus R. Suppose beta equal to 1, this is F beta. This we can call it as F beta equal to, this is the harmonic mean of two variables P and R. When beta equal to 1, we know that it is 1 plus 1 into precision into recall by 1 square precision plus recall. That is given by 2 into precision into recall by precision plus recall. So when false negatives and when both false negatives and false positives are important, then we should take F1 score equal to F score is equal to, we have to take it as consideration as 1. Beta should be equal to 1. Okay. When both false positives and false negatives are equally important, then beta should be equal to 1. If only false positive is more important, then we should take beta equal to 0.5. And only false negatives are more important, then we can take beta equal to 2. Like this, different variations of beta we can use as per the importance of these false positives and false negatives. So this is what about the confusion matrix and the evaluation matrix, how we are going to find out especially accuracy, precision, recall, and the last one is the F1 score. Thank you.